Okay, hello, welcome back everyone. So could I just get a show of hands whose TA showed up for tutorial? Okay, so the majority, did anyone's TA not show up or were they late? Okay, good. Okay, I've been in contact with your TA. They now know where the room is. I guess they were late, but I'm late, so I can't fault them too much. Okay, so there was a observation I just wanted to share with people. So if we go to the blog, there's a wee bit of an update here. Several people spotted a typo in question 2.5 of homework 1. Thank you, those people. That is amazing. Thank you for spotting the typo. What did it say? It asked, express the vector ijj as a linear combination. This is kind of weird, right? This is sort of not what we'd expect. We'd expect ijk, right? This expression ijj is unsimplified. Okay? So if you look at the homework sheet, this typo has been fixed. Okay, so it says ijk, and that typo needs a little bit of a correction. Okay, so thank you people who found that. If at any point in this whole course you think there's a typo, please let me know. Okay, please just send me an email. Be like, I think this is a typo, because in math they're very, very, very hard to find, and it's very helpful when people find them. Okay, any questions about that? Yeah?
I think it should be, like, in that question as well, I think it should say K is equal to 0 times A plus 0 times B plus 1/6 times C.
Perfect! Even more typos! Great. Yes. Right, so C, if I take 1/6 of that, I should get K. All right, so this is what happens if you copy and paste from yourself. This is plagiarism from myself. Okay, that'll be fixed too. Very good. Okay, awesome. So let's imagine that we have to express this guy as a linear combination. Okay, very good. So that's what we needed that for. Good. Oh, dang, I shut it down. One other thing, if you're interested in learning LaTeX, I put the LaTeX source code for the homework assignment up. So if you know LaTeX, the source code's available also on the blog post. Okay, so if you don't know LaTeX, it'd be a fun document to play around with. Okay. Okay, so what are we up to today? Today we're going to do sort of two things. Our first topic is going to be determinants for a long time, and then our second topic is going to be the cross product. Okay, the cross product, I guess, is sort of like the first really sort of calculus kind of thing that we're going to get into. All right, so let's get into determinants. So, first of all, we need a definition. Okay, the determinant writes as follows. Okay, so when you write sort of vertical bars like this, you can also write it like this. And it's the following thing. Okay, so it's sort of an absolute value associated with our guy. Oh, I didn't put the thing on? Okay, thank you. Yes, good. Sorry, I didn't put the thing on. Is that good? Yeah, that's better? Okay. Okay, so this is the determinant. What does it do? What's the point of it? Okay, so now here I'm going to introduce a concept of the determinant you might not have seen before. Okay, the determinant measures the area of a parallelogram. Okay, so often we think of it as something about invertibility of matrices, but I think that the geometric way, or the kind of more fundamental way, is as a particular area. So the area that we're measuring is as follows. So if we've got this matrix A, B, C, D, then these two vectors here, AC and BD, right? These guys are the image of the standard basis under our matrix. So what does that mean? Right? If we've got ABCD and we multiply it by this basis vector, we get AC. If we multiply it by this basis vector, we get BD. Okay, so what do these guys mean? This is the matrix takes the first vector to A, and it takes the second vector to B, basically. Okay, so we get these two guys as the image of the standard basis of the plane. And they form a parallelogram as follows. Right? So if we extend those guys into a parallelogram, then we've got some area here, A, and our fact is that the determinant measures the area of A. Okay? So often we think of this as a thing about invertibility. Can anyone see how to get invertibility from this area fact? Right? What happens if we've got a non-invertible matrix? Yeah?
Got no area.
That's true, yes. Why does it have no area, though? Yeah, there you go. The basis vectors become parallel. All right, so here's our little theorem. Okay, if the determinant is equal to 0, then our matrix is not invertible. Why is it not invertible? Well, we start off with our basis vectors here. Right, so here's our square before we apply the linear transformation. right? And if we apply a thing of determinant 0, then there are sort of two possibilities. Okay, either all of space gets mapped down to a point. Okay, so that's where A is equal to the 0 matrix, and that squishes everything down to a point. Okay, or we make the two basis vectors parallel under our linear transformation. Okay. In both of these cases, we've got determinant 0, right? So determinant 0 means we're either a point or we're a line. And in both of these cases, we can't invert the matrix. We can't go from a point back to the point we started at. We can't go from 0 to a point in the plane. Okay, so those are sort of our two cases where we have determinant 0. So the area of this thing gets mapped to something of area 0 and something of area 0, and that makes our matrix not invertible. Okay, so very good. Okay, so now we've talked a little bit about what happens with 2 by 2 things. So let's think about what happens with 3 by 3 things. Okay, so the determinant of a 3 by 3 thing works as follows. Okay, so we've got our 3 by 3 grid of numbers. Okay, so here's our sort of our ugly and out of a hat formula for the time being. Okay, so we can get 3 by 3 determinants as sort of a combination of 2 by 2 determinants, and we're going to talk about what combination that really is. Okay, any questions so far? Or any typos spotted? Yeah. What about a parallelogram in 3D space? Good question. Right, so our sort of sticking with this idea of area, we get the following fact. Okay, so parallelograms aren't especially, they're not like the best things in the world. They're not very important. So this fact shouldn't just be about parallelograms. It should work in all dimensions. So let's say in all dimensions, Okay, in all dimensions, the determinant measures the volume, okay, of a parallel something. So I think it's pronounced parallelepiped. This is one of these words that I've only ever read in English. I don't say it very often. So I think this is called a parallelepiped. If we could get someone with a dictionary or like could get their computer to say it, that'd be really helpful. Okay, so this is our corrected theorem, and we have to think about what it really means. Okay, so the first thing is we have to get a handle on what is the generalization of a parallelogram. Okay, the parallelepiped okay. So the parallelepiped formed by the vectors ABC emanating from the origin, let's say of R3, is the following thing. Okay, so it's all possible combinations of A, B, and C, or all possible linear combinations of A, B, and C. Okay, so let's say these are our vectors A, B, and C. Then the parallelepiped is the box formed by those vectors. Okay, so each side of this thing is parallel to B, or to C, or to A. Okay, so it's sort of all possible linear combinations with there's a bit of a detail missing. Okay, are there any questions just about this picture so far, though? Okay, so it's oops. ST. Okay. So does this formula describe this box at all? Is there something odd about this formula? Yes?
Shouldn't the magnitude be like constrained somehow?
Yeah, right. So if I just leave these guys unconstrained, then A can get very large. Yeah? So A could stretch all the way out here. So it's not all possible combinations. How do I want to limit the possible combinations? Yeah? Yeah, sure. So all possible combinations where S is in 0, 1, T is in 0, 1, and U is in 0, 1. Okay, so now what will happen is we won't be able to stretch A farther than it originally starts. Right? So we can start at any point and move at most one copy of A. Okay? So that describes the shape for us. And we can write this down in any dimension now. So not just in R3. Okay, the parallelepiped spanned by V1 through Vn in Rn is let's call it P. Okay, so that's our definition in Rn now. So we add up Ti times Vi, and we constrain the Ti's to live in the range 0, 1. Okay, so that's the parallelepiped for us. And now we have this fact that I think says something really deep about linear algebra. The determinant measures the volume of a parallelepiped. Okay? Yes, sure. Yeah.
Why do we need those coefficients?
Right. Yeah. So why do we need these coefficients? Because we want to just describe with a formula this finite box. If we allow any value of s, then we could stretch a over here or something. But we only want to limit ourselves to this small box. Right, so this is kind of like, so what does ABC mean? Right? A plus B plus C would be this point here. Right? And if we just wrote A plus B plus C, we'd only get this dot. Okay? So we introduce the coefficients to fill out the box. Yeah? Any questions or thoughts so far about that? Okay, so the fact I'm trying to say is okay, the determinant of M, or here let's say the determinant of a bunch of column vectors v1 through vn is the volume of P Okay, so that's our restatement of what the determinant measures. Okay, and now we have this really, really nice interpretation of what it means for a linear operator to be non-invertible. So if if a matrix is not invertible, then it takes the whole of space and pushes it down to something lower dimensional. So in 3 dimensions, you can push down to a plane, a line, or a point. Okay? All 3 of those will have no volume, so they won't be invertible. Okay, very nice. All right, so now I want to say some sort of algebraic facts about determinant or how to calculate it. Okay, so this is sort of going to be our main tool for calculating determinants. Okay, and it's the so-called cofactor expansion. So our goal with this thing is to calculate determinant of M. So we're going to introduce some coordinates on our guy. Okay, so these are the entries of our matrix. So these are the MIJs. Okay, and now we're going to define this matrix. Actually, you know what? I'll make sure that I follow the notes exactly. Sorry. Sorry. This is M. Okay, so we've got M, and then we're going to write M twiddle ij for the following matrix. Okay, so this is the this is the matrix M with the row I and column J removed from it. Okay, so it's a slightly smaller matrix. And now we're going to do a little bit of recursive programming. Okay, so define the determinant of a single number. So we've just got one number A. We're going to define the determinant of A to be A. Right, that's pretty reasonable. And then, for all other determinants, we're going to define them this way. Okay, so that's good. Okay, so this is our definition of a determinant. So it's a recursive definition. So we define it for 1 by 1 matrices. And then to define it for an n by n matrix, we define it in terms of n minus 1 by n minus 1 matrices. Okay? Yes, sure, yep. Is it negative 1 to the power of... Oh, sorry. Right, yes. So these are 1s. Okay, I fixed those to be 1s. So if we were just doing it along a general row, if we were doing it along the row I, you'd be right. Yep.
Shouldn't that sum go along J, no I?
Because there are no i's involved.
Yeah.
Yeah. Very good. And this is why you should follow the notes exactly. Let's see. Is that exactly what's written here? Yes. Good. Okay. So the sum is over J, and we go as follows. Okay? So before anyone asks, yes, you have to memorize this. Okay? It's an important formula. There'll be no formula sheet. You'll need to know it. Okay? Good. So this is our cofactor expansion, which gives us determinants in all dimensions. So let's see how this actually looks in practice. Okay? On paper, it's very scary, but in practice, it's not so bad. there. Okay, good. Okay, so this is the kind of calculation that we'll do using determinant. And we got to think about what this, this recursive formula means, right? So we've got a 3 by 3 thing, and we're going to express it in terms of 2 by 2 things. So what do? We focus our attention on the first row. Okay, then we take that entry 1, we multiply it by this, so we put our coefficient, -1 to the 1 plus 1, times this entry here, times the following determinant. Okay, so what do? We take this guy and we delete the first column and the first row. Okay, so now let's do the second entry in our sum. Okay, so here in the second entry of our sum, we delete the first row and the second column. Okay, and now we delete the first row, third column. Okay, and we get the following thing. Okay, very good. So when we delete these rows and columns, we get smaller matrices. Yes, good. Yes, because it's -1 to the 4. Sweet. Okay. So there's our recursive formula in action. We've expressed the 3 by 3 thing in terms of a bunch of 2 by 2 things. Okay, so what's our next step? Now we can use our 2 by 2 formula. If we really wanted, we could use the recursive definition again, but let's just use the 2 by 2 thing. Okay, and then these guys have have columns of zeros. Okay, so we get our final answer of 24. Okay, and just for the curious, okay, this is my favorite number. Okay, it's probably the most interesting number. I'm not quite sure. But yes, if you ever ask me about 24, I will lecture for like an hour. It'll be a complete disaster. Okay. Oh no, what have you done? So why is 24 great? First, if you multiply the numbers 1 through 4, they multiply to be 24. It's pretty interesting. How many rotations does a cube have? Distinct rotations. 24 distinct rotations for a cube. What else is interesting about 24? We know the optimal packing dimension constants in dimensions 1, 2, 3, 8, and 24. That's the only dimensions we know. So anyway, very interesting stuff. Okay, sorry, I'm totally sidetracked now. Okay, 24 is a great number. We need a couple algebraic facts that I just want to write down quickly about this thing. Okay, so our algebraic fact about determinants. Okay, so there's the example. Okay, so we need a couple algebraic facts about determinants. Okay. Okay. So how does this thing work? It plays very nicely with row operations. Okay, so what does that mean? We have the following facts. So if we take a matrix and apply a row operation, okay, so if we take the matrix A, swap rows I and J and get row B, or sorry, get matrix B, then we pick up a minus sign. Okay, so a very easy fix. If we multiply a row by k, then we get the following. Okay, we multiply by k. Good. And then our last row operation if we add k copies of one row to another, okay, so this thing works really, really, really nicely with row operations, which is good. Our other key fact about the determinant is the following. Okay, so this is a fact due to William Hamilton, a major player in our textbook. Okay, the major fact that we need is that the determinant splits across products. Okay, if we have A times B, then then we get the determinant of A times the determinant of B. Okay, so this is super duper 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 helpful. I just want to show the power of what we use this for. Okay. So the first is that these things give us a very nice way of calculating determinants where we can skip a bunch of stuff. Yeah?
For the second operation, it's supposed to be that A equals R to B.
For number 2? No, we definitely want a k here. Okay. Yeah, we really want that if you multiply everything through by a number, the determinant gets multiplied through by that number. Okay. Yeah, cool. Good check. So the power of this is that it lets us, yeah, sure.
What about number 3?
They actually just equal.
No, I mean like R I plus A R J. They all equal to
Right, so for these, so if we add k copies of row j onto row I, then the determinants stay the same. So the two things will have exactly the same volume. Okay, so yeah, so what this means is we take this matrix, add k copies of row j to row I, and we get this matrix. Okay, let's do an example to see how this stuff works. Okay, so now instead of this huge, long recursive formula, we can use these algebraic properties to figure things out. Okay, so we can subtract rows from each other, and the determinants are going to be equal. Okay, so if we subtract row 3 minus row 1, we get 4, 5, 6. Okay. Okay, and now instead of working with this expansion that has a lot of sums, we can just use algebraic properties to calculate this thing. Okay. Okay, and now this whole top row is all zeros, so we know the expansion will be 0. Okay, yep.
Shouldn't there be a minus?
Oh, yes, there should be a minus. Yes, good. Good. Yes, when we use this row switching operation, according to fact 1, we have to introduce a minus. Yeah, good. Any other questions or comments? Okay, so this is very nice. And then the other key fact about determinants that we can get from Hamilton's theorem is this. Okay, so this is sort of our key fact about invertible matrices. So how can we prove this using what we know about determinants so far? Hamilton's theorem and all this stuff. Any suggestions for the proof? Yeah?
So we should be able to say that the determinant of the identity matrix is 1.
Yeah, sure. It's a little bit of a lemma. Yeah.
And then from there, we need to be able to say that the determinant of the matrix times the determinant of its inverse has to be equal to 1.
Okay.
One of them is 0.
Yeah, if one of them is 0, then it won't happen. Yeah, exactly. So okay, so we know that these guys multiply to give us the identity, right? This guy's invertible, so there is an A inverse that we can do this with. Okay. Yes?
From this, can we also say that the determinant of the inverse equals 1 over the determinant of the original?
Yeah, yeah, we can get that from this too. Yeah. Okay, very good. So we obtain that this thing is equal to 1. We've got a product of two numbers, right, equaling 1. So neither of those things can be 0. Okay, so thus we get that this product, this determinant can't be 0. Okay? Sorry, why did I write? Because he proved it the first time. So this theorem is he proved that a long time ago, I think. Yeah? Okay. Right, so just, who does this stuff? People do this stuff. So it's important to know who did what when, especially big, important theorems. Okay, so where are we at time-wise? Okay, so it's now 10 o'clock. We'll take let's say a 10-minute break. Some people were complaining that I went over time, so I'm going to set an alarm. Okay, so I'm not complaining. People observed that we went over time on breaks. Okay. Okay. So are there questions or, she's just making a hand gesture. Okay. All right. So we talked about determinants, and now we're going to move on to the cross product. Okay. The cross product is probably one of the nicest things that happens in 3 dimensions. It's a very, very, very surprising formula. So I'll show you how this thing works. Okay, so the cross product has the following properties. Okay, the cross product is only defined for vectors in R3. Okay, it's a very, very, very 3-dimensional kind of thing. So we'll just deal with it in R3. Okay, the first is that it has this length. Okay, so in this way, it's very similar to the dot product, right? With the dot, we had u dot v is u v cos theta. Here, we've got u cross v is u v sine theta. Okay, very similar looking formula. And the other point about it okay, is that it is orthogonal. So it's a thing that generates orthogonal stuff. Okay, so it has this length and it goes in this direction. There's a bit of a tricky point here about the orthogonality. Can anyone see the tricky point? We've got two choices for how, these guys are losing it. Now I'm losing it. I don't know. Something is incredibly funny over there. Okay, so it's orthogonal. The difficulty is that there's two ways to be orthogonal to a pair of vectors. So if we've got a plane like this, we could imagine two vectors living here, right? And now this direction's orthogonal to those two vectors, right? When I come out of the table, I'm orthogonal to the red pen and the blue, the green pen. Okay. However, I could also be orthogonal in the direction below the table, right? So I could come up like this, or I could go down underneath the table. So I have two choices of a vector that's orthogonal to both of these at the same time. So we have to make a choice. Okay, so it is orthogonal to these two vectors in such a way that if we were to look at it from above like this, with u and then v, the cross product is here and it points out of the page. Okay, so u cross v points out of the blackboard. Okay, one way for remembering this choice of orientation is the so-called right-hand rule. Okay, the right-hand rule says that if we start at u and curl towards v, the thumb should be pointing in the direction of the cross product. Okay? So if we start at one vector, curl our fingers to the other, the thumb is the cross product. Okay? Okay. So that's all fine and good about this right-hand rule and this cross-product business. It's more important, though, to have a formula for how to calculate it. Okay, if we've got our vectors in coordinates, okay, and now this is a very, very strange formula. What's strange about it? It almost looks like a typo. Yeah.
IJ and K are vectors.
Right. Yeah, they're vectors. So what are they doing as acting like numbers? Right? So what we're going to say is that these guys are what are sometimes called formal variables. Okay, we're going to treat these guys as though they were variables. So let's see what that really looks like for calculating stuff. Okay, so for really calculating stuff, let's do an example. Okay. Okay, so let's calculate this in two ways. Okay, so first, let's calculate it using this right-hand rule business. Okay, so using the right-hand rule, we should draw a picture of the two vectors that we're putting in. Right, so this will be u, and this will be v. Okay, so now the question is, are we going to get 0, 0, 1, or are we going to get 0, 0, negative 1? Should the vector be pointing sort of out of the table or into the table? What do you think? So maybe take 30 seconds, draw a picture of these, and try with the right-hand rule. Okay. Okay, so here's our setup for the right-hand rule. Yeah. So I've made it with our highly scientific pens. And what do? So here's our vector u, here's our vector v. We take our right hand, we put it over top of the intersection, and we curl our fingers from u to v. So it's pointing up. Okay? If we do that on the blackboard, then we start here, we curl our fingers from u to v, and then we're pointing upwards. Right? So this should be something, and it should have positive z coordinate. So we're going to guess, educated guess, that we get this. Okay, are there any questions about how that calculation goes with the right-hand rule? I remember when I was in high school, they taught us this, and I skipped that class, and it came up on a test, and I was like, the right hand, does the vector point into or out of the page? Like, I was just completely confused. So I hope that you do this exercise and remember, because it's very strange when a math test asks you about your hands. Okay, so let's calculate this thing. Okay. So using our formula involving the determinant, we have to be careful to work with these formal variables. Okay, so we're going to get I minus j plus k. Okay. So we get, so this is the sense in which these are sort of formal variables. We just treat them like they were a symbol that can kind of get pulled in front of things. Okay? We don't actually care about their entries. So then we get okay, so we get k, which is the guy we were looking for. Okay, any questions about that calculation or thoughts? Okay, so that's the formula for the cross product. Good. One of the things that was asked in the homework. Okay, one of our questions was calculate this guy here. Okay, so in order to calculate it, there's sort of a two-stage thing. First, we're going to convert these into numbers. Like this. And now we're going to apply our cross product formula. Like this. Okay, and now we can calculate the coefficients directly. Okay, so here we get negative 3i plus j plus 5k, I think. Okay, could someone check that for me? Yeah? 5i? Yes, good. No, wait. Wait, I was right the first time, negative 3. And then where's the 5? It's k? All right, let's double check with the notes. Yeah, that looks good. Okay, so very good. As you can see, there's a lot of room for typos here. So let's figure out a way of checking. Is it negative j or positive j? 1. Well, let's check. Let's find a new way of checking. Okay, so if we find a cross product, we know it's orthogonal to the things we put in, right? So Right, so if we check this cross product, or sorry, this dot product, it should be orthogonal, right? So what we're doing is we're checking this. Okay, so we get -3 minus 2, 5, which is 0. Okay, we got that one. And now we have to check with B. So we get -6. Did I copy it down wrong? -6 plus 1 plus 5. Okay, good. So we are happy on both counts. Okay, our thing is at least orthogonal. Yep. Sorry, so it's 1 minus 2, 1. That's this guy. And then it's 2, 1, 1 for the other guy. Is that okay?
I mean, for the cross product.
For the cross.
C plus A plus
So this should be -3, 1, 5. Yeah? Okay. Good, good, good. So that's how. Okay, so sort of a geometric interpretation of this magnitude. Okay, the area of the parallelogram is A cross B. Okay. So this is sort of a geometric interpretation of what this quantity means. Okay, so if we've got two vectors and we form that parallelogram like this, then we get A cross B. Okay, so the area of that region is the length of the cross product. So a friend of mine works in computer graphics, and I said, "What's up with cross products?" So yeah, it's sort of strange. He did one of these like coding boot camps. So he went to BrainStation, if anyone's heard of BrainStation. And he did the whole training thing. He got like, you know, his elite hacksaw skills. But the guy's an English major. Don't tell him I told you. So he becomes a computer programmer, and then he goes to work at a company that makes 360-degree cameras. So it's like a GoPro, but it records every direction around the GoPro. So like the idea is that you hang these things off kites and stuff. Anyway, my friend learns how to code, goes to work at this company, and then suddenly he has to deal with like cross products and quaternions, which we haven't even talked about yet, and all sorts of like really, really intense vector calculus to do motion capture on these cameras. So I asked this guy, I said, what's up with cross products? And he said, there's two interesting things about the cross product. First, okay, the first thing is that it gives you a normal. Okay, so on this picture, the normal to the plane spanned by AB is here. Okay, so the first thing is that it tells you, according to the right-hand rule, that that's the normal. And the second thing is that it gives you an area in terms of length. So he said that the place where cross products most often come up in computer graphics is where you want to figure out how much light is hitting a surface. You need to know the direction of the surface, and you need to know its area. So if you're doing like a computer simulation of shading or something, or shadows, you need to know the surface area, and you need to know the direction. So that's a place where the cross product is kind of used. But OK, so that's our fact about what this thing can do. OK, so let's see a calculation using this. OK. Very good. So let's calculate the area of this in this kind of cross product way. So we start off here. OK, so those are our two vectors, A and B. And then this is the parallelogram. So its vertices are here. And then what's this one? This will be at 2, 1, 0. OK, so we want the area of this shape. Oh. OK, so let's calculate it using the cross product. OK, so the area is something like this. OK, so we're going to get OK, so I think that's the correct thing. Could someone take a moment and verify that? Just quickly do the check. Yeah, good. OK, I've got a couple thumbs up. 0, 0, 1. OK, good. So this is 0, 0, 1. OK, good. So our area is the length of this guy. Okay, so our thing had total area 1. Okay. So just to look at it again. Right? And we can check that area because if we cut here, this will have height 1, height 1, height 1. So we can reassemble the thing to make a square if we want. Okay, yeah, so that's the correct value for that. Okay, are there any questions or thoughts about cross products? So far, so good on cross products? Yeah, sure.
Also, like the maximum truth, you get 0, 0, 1, right? But you can get like 0, 0, minus 1.
Yes.
But then you use the right hand.
Right. Okay, so concerning area, if this is 1 or minus 1, the area doesn't know. The area is the same for both.
I just mean like in general.
Yeah, so in general, so here, right, so we would get, if we switch these, right, if we switch the order, we get a negative sign. Does that help?
No, I just mean how is the right hand rule? Like, how do you apply it?
How does it work? Yeah, so this is always the first vector, this is always the second, and then you go from here to here. Okay, so it's most useful in pictures in the plane, right? Because then you've got a very simple picture to look at. If you're in space, things are a little bit harder because then it's not clear what plane you have. But you take the plane given by these two vectors. You take this plane, look at it from above, and then right hand rule.
So if this goes out, like if it's negative, like it goes in.
Yes.
Do I change the sign?
Yes. Yeah. Good. Yeah.
I change the sign.
Yeah. So the sign. Yeah. The sign would go from positive to negative. Yeah. Good.
If it's negative, then I get positive.
Yes. Yeah. Change the sign. Yeah. So up is positive sign. Down is negative sign. Good.
Not necessarily negative. You just change the sign.
We should talk about this in office hours. This is a good point. It's a subtle point. I guess the nicest way to summarize this is if you use right? If you use this formula, it'll give you a sign, and that is the correct sign. Right? So always yeah.
Okay, so if I use this, then I won't need
Then you won't need to change any signs. Yeah, so this always produces the correct one.
so if I use this, I won't need the right hand rule.
Yes, yeah. So this needs no right hand rule.
So which one use the right hand?
When you're given sort of a picture in the plane or something. Yeah. Okay, so the main place where we really use the right hand rule is when we're calculating a certain kind of derivative, and we'll get there. We're not there yet. Okay, are there any other questions or thoughts about this? So the main thing here is this always produces the correct sign. The right-hand rule is useful for doing calculations with pictures in the plane. Okay, so last Thursday we did a little bit of a summary. I want to summarize again what we did this week. Okay, so what did we talk about this week? I can't even remember what we did on Tuesday. Yeah.
Determinants and crossproduct.
Okay, yes, definitely. Yes, all right. Okay, good. We definitely talked about determinants and cross products. What did we talk about on Tuesday? Matrices, matrix multiplication. Yes. Okay, so one of the things that I wanted to emphasize with matrix multiplication was this dot product interpretation. Right, so we had several versions of that. What else did we say about matrix multiplication? Yeah? Yeah, the matrix inversion algorithm. Oh yeah, and anytime I say algorithm in this class, you should think about coding it and putting on GitHub, okay? You'll learn these algorithms much better if you code them. Okay, so the matrix inversion algorithm, matrix inverses, anything else from there? Yeah, sure.
Transpose.
Yeah, transpose, yeah. Actually, here, I'll say this. Okay, so our dot product business was that we can transpose and multiply. Okay, any other things that come to mind from the week? So what else did we say about determinants? There was tons of stuff about determinants. Yeah?
The cofactor expansion.
Yes, cofactor expansion. Right? That's our key tool for calculating these things. We did volume of parallelepiped. Okay, what else? Yeah? Yeah, Hamilton's thing. Yeah. Oh, by the way, that has a really nice interpretation in terms of volumes. So in terms of volumes, what it says is if you apply the matrix A, if you apply the matrix B, that takes the cube and changes it into a thing of volume determinant B. Then, if you apply A, it stretches again, and that effect is multiplicative. So if you apply the transformation B, you stretch volume this much, and if you apply the transformation A, you stretch volume this much. Okay, very nice interpretation of the result. Okay, what else did we say about determinants? Other useful things?
Row operations.
Row operations, yes. Algebraic properties and row operations. Okay, and then one that's so obvious that only I can say it is invertibility. Okay, something is invertible if they has non-zero determinant. Okay, for the cross product, we had the right-hand rule. We had a formula. Area of parallelogram. Okay, any other thoughts on the cross product there? Other uses for the cross product? Oh, one other thing that it does is it helps us find normals. Okay, good. Very good. So yeah, I would say that's a pretty thorough summary of the week. Okay, are there any questions that came up? I saw some people wanted to go over a midterm question. So when we did the survey, are there any questions people have just in general? Yes.
For the determinant formula, it seems like you made it so that we always have to choose row 1.
Yes.
You can choose any row, right?
You can choose any row as long as you switch it for the first row. Yeah, you have to pay that -1. Yeah. Okay. Good. Any other questions, thoughts? Oh, I promised you guys a nicer solution to that problem. Right. Okay. Oh, yes. One other thing. If you take PDF notes, it'd be very, very, very helpful to have them. Someone's already sent in PDF notes for last week. That person is a hero. Thank you. So if you take notes on a tablet or something, please email them in. Okay, then we can have a good record of what happened. Okay, yeah, so if you take notes, please send them in. Right. Okay, everyone's kind of getting antsy and about to leave. For those who want to stay, I just want to offer a nicer solution to that question we did last lecture. Okay, so at the end of last lecture, we solved this problem, but it was kind of difficult because we had to find a line kind of out of nowhere. So can anyone see a nicer way to do this now that we have determinants and cross products? Yeah? Yeah, sure. No, you had a question? Okay, cool. Yeah, over here.
Try to find a determinant, and if it's 0, then this is not invertible, so it's kind of like on one line.
Yeah. Okay, good. So the idea there is if we've got 3 vectors in space, right? If we've got 3 vectors in space that determine a unique plane, right? Then we can put a plane on top of it like this, right? And it'll just sit there. Well, maybe it'll sit there. So if they determine a unique plane, then there should be a parallelepiped right here. Right? That parallelepiped will come out and will have some volume. So let's try and calculate what happens to the volume of these guys. So the idea there is thank you for shushing. You're doing good work. Okay, so we look at the volume of the parallelepiped spanned by those guys. Okay, so now we have to do some determinant calculation. Okay, so how should we calculate this thing? Yeah? Yeah, row reduce, right. So I've got a leading 1 here, or I've got a leading -1, so I'm going to... Okay. Okay, so those 2 moves just put this into a way to use it as a leading 1. Yeah? Okay, so now let's continue. Yeah. So now we'll add 2 copies of row 1 to this guy. Okay, now we've got a leading 1 here, so we'll subtract off 4 copies. Okay. Okay. So our parallelepiped has volume 0, so it can't support a plane. Okay, so okay, very good. So that's a way of doing that same thing with the determinant now. Okay, yep.
You listed them as column vectors. Does it matter if you list them as row vectors?
No, it'll work out both ways. So that's another fact about determinants that we'll get to eventually. Yes, indeed. Okay, let's just write it down because we can't hint at it. Okay, any other questions or thoughts? Okay, folks, so if you're taking PDF notes, please send them to me. It'd be very, very, very helpful to have them. All right, work hard on the homework. Thank you for finding the typos. Yeah, have a good Victoria Day weekend, everyone.